Ladies and gentlemen, I'm happy to present you today our novel lightweight design methodology for die-casted housings, what we have applied on a gearbox cover, and I will explain you now how this will work. So let me first give you an overview about what we did. We designed a new gearbox cover, and we had a reference structure from aluminum with a mass of 2.5 kilograms. And if you substitute this material with magnesium, you end up with a weight saving of about 25%. But what we did was that we developed and applied a new novel design methodology, and we achieved additional mass saving of about 34%. I'm going to explain you now how we reached this. So we started with analyzing the weak points in today's development process for die-casted housings. So in the first step, a designer typically decides on the functional concept. So he decides on the rough shape and the design space. And this means that he is positioning the flange and the bearings, and he's covering the components he likes to cover with this gearbox housing, for example. And the problem here is that this is the basic information which he is using to then define a design space for the topology optimization, which gives him then a rib pattern what he can apply. So the problem here is that the loads and the requirements here will be considered not earlier than in the second step and not in the first step. And the typical process ends then with a detailed design for castability. That's something what we are also doing in our methodology. But the problem, what we see here, that the only roughly designed shape in step one influences the result of the topology optimization much more than typically estimated. With our design methodology, we focused very much more on the first design step. So we did a detailed analysis of the relevant force vectors in different load cases. Then we looked and designed a load transfer concept of the part. Only a concept, not with doing any design in this step, but we said where do we need material to transfer the load between the bearings, for example, or between the bearings and the flange. What is the optimal shape? And we saw that it's much better to have a kind of a three-dimensional tent-like shape and straight directions between the bearings instead of bending related design what we had before. And with this optimized design concept, we do the next two steps. We go into the topology optimization and then the detailed optimization for castability. I'd like to give you an example. The question is, how much material do we require to safely transfer the forces between the bearings? We have calculated this with a typical load for such a part with 20.4 kilonewton, and you find that we need a straight bar of, with a diameter of 18 millimeter. And this means we have a weight of such a straight connection of about 48 gram. And if you compare that we have started with a reference weight of the fully component of 2.5 kilograms, we have a huge potential if we optimize the load transfer. So increased material utilization and the design for force flow is a very important measure to improve our part designs. Let me give you another example. We have here a typical cover shape. It's a generic part, what you can see with a flange, with a cover, the yellow part with a bearing and with some ribs. And if you change the material or move the material to a place where it carries more loads, like an alternative design like this, you have the same number of ribs, but you have changed your design. and moved yellow material to the red areas here, then you have significant effects. Like in this load case, we have a reduction of stresses of about 11%, and in another load case, we have a stress reduction of about 50% and a reduction of the deflection or deformation of minus 45%. So there is significant potential in the way how we utilize our material, like mentioned before. So finally, I like to show you the design of our gearbox cover. This is the casted part with the optimized design. And as I mentioned before, we started with an aluminum reference with a weight of 2.5 kilograms. And our final magnesium part has a weight of 1.23 kilograms. So we saved about 51% weight. And 34% of weight saving is coming directly from our new design methodology. And I like to thank all the partners of this project. It was a very strong consortium which worked here together. Thanks again, and thank you also for IMA for the opportunity to present here. Thank you. Bye bye.